Okay, thank you. Thank you so much for your introduction, and really thank you so much for inviting me. And this is my very first virtual talk. So please let me know if you cannot hear anything, any technical difficulty or any math question. Today I'm going to talk about, like the title said, polytopes, wall crossing, and cluster varieties. My main focus of today will be this joint work. Yes, you can see I have technical problem immediately. Okay, this joint work. The main focus of today is this joint work with Tim Magee and Najera-Chavez, Najera-Chavez, which what we do is we describe the compactification of cluster variety by something we call convex-like convexity. But I just wish to convince all of you why we care about it, or why this spoken-like convexity is a really good notion of it. So we'll spend some time to discuss like how we can work it on Grassmannian. That will be a joint work with Lara Bossinger and again with Magee, Najera-Chavez. And then the idea behind when we start working with this polytope is we want something like Batyrev duality, and that this is something we'll go a bit about what is our idea behind working on all this polytope thing. And then but all this thing we are just working on the algebraic geometry side of mirror symmetry. So at the very end, as I'm not going to be too much detail, but I still want to give you two pieces of evidence or support why we care this polytope or wall crossing structure, which we can also say something in the symplectic world as well. So let's just get started. The analogy is we'll start with, we call some notion in Torah geometry, which is we'll have a lattice and then a dual lattice, NR and NR, which is basically Rn and Rn. And then let us recall how we define a projective toric variety from a polytope, which we start with a lattice polytope in the lattice NR. So what we do here is we'll define a greater ring greater by t, but the thing, oh sorry, it should be n, but it is n anyway. So here, usually the picture is we have this polytope delta here, and then we move one high dimension, which is we are thinking at level 1 here, and then we define a cone, and then here is the t there. The way we think is like when we multiply 2 pawn and the 2 different lattice, that is, we have this polytope at level here k and l, that is indexed by the t, k and l, and n point. So when I multiply them, my monomial n plus n point must be in the k plus l polytope there. So you can see that's why we need convex as a condition of the polytope. But you can see here we can give a greater ring, and that as an algebraic geometer, we just take Poch, and then we have a projective toric variety. And then if you are cosmeticistic people, this is chapter 2. And then what chapter 3 is, we just go to affine toric variety, which we have a fan, and then we just, each fan give us, each maximum cone give us the affine toric variety, and we go along the intersection, and then we have an affine toric variety, and then put a pawn on the fan. We can associate a toric monomial which describes the range of this affine variety, and this is kind of this duality between the fan and polytope with a support function. So this is what we do in the Torah geometry. So what I'm going to convince you today, or in the first part of the talk, is we can develop this energy, like this cluster world and the toric world are very, very similar. So again, we start with a lattice. Let us first define what's meant by a cluster variety.
Maybe can I quickly interrupt you? So there's a question. So
sorry.
When could you maybe just unmute yourself and ask your question?
Oh, sure, of course. Yeah, I raised my hand just because I can't use the chat channel. I don't know why. It says that the chat channel is only available to team members, so I can't use that. But anyway, so do we require the polytope to be at least like a normal or ample?
Well, we don't need to be ample. Okay, here is just an energy, like as long as we do need normal.
Because oh, sorry, go ahead.
But the thing here, I just want to say, because we are going to do the cluster, the thing is, as long as we have this convex polytope, then you can see we have a graded ring, and then we have a projective toric variety.
Okay, I see. Great, yeah, thanks.
Thank you so much. Let me go back. Oh, am I sharing or not sharing? Sorry, I'm really sorry. Okay. Okay, I guess you can see the screen. If not, then yell at me. And then, like, I just want to look at an analogy in cluster variety. Again, we start with lattice n, but if you're like here, because I'm writing slide, I want to be very careful. There might be some scaling there, but you can just think it's just technical difficulty, like for technical reason. But you can just think I have answered it's just n, and then the lattice is m, and then it is like then we look at the torus to the lattice, and then what we define this, what we call the A cluster variety, is a collection of all those torus, and we group by some birational map we call mutation map. We are going to go over the example, but if you're unhappy now, think of it as something 1 over x is birational, because when we do inverse, we need to divide 1 over x, and then x is similar, it's just on the dual lattice, which we have a bunch of torus, and then we group by something we call the x mutation. If you are a cluster people, the way we can see is those torus are correspond to the seed, and then those rational map are just correspond to the exchange relation of cluster variable. But if you are algebraic geometry who don't care about cluster, then you are just, those are a bunch of torus, and then there's some rule in combinatoric tell you how the birational map is. And then here, like the first thing is, an analogy is I want something fan, like I keep on, it's like double and triple bracket. But the thing I propose is very similar to fan in something called scattering diagram. Scattering diagram is just a collection of wall. It's like fan, it is a collection of cones with some finite condition that, if you like, I can tell you the details afterward. And then, but then what's this mean by a wall? A wall here is we have two data. It's not like the usual cone that is just the way the hyperplane, but we still have it. We got D, we call support of the wall, which is coming from some convex rational polyhedral cone of codimension 1. It is counting, you can kind of think it's hyperplane in some sense, because I have a normal of this wall, and then this f is a function. If you want to write out is something like this, I know I didn't define p star n, but I just want to tell you that because this wall is lies in the normal of this n, and then this fd is some polynomial or power series with variable associated to this normal, and that is what I want. That is the only one thing you need to remember for what's wanted. And let's go, for example, this is what customer we are going to call a A2 example, which you can see because it's dimension 2 here, and then the wall dimension 1 will be just a line or half line that is away, and then I have those functions that associate to the wall. And as I say, I want to have an analogy of scattering diagram as fan. Torah geometry, do not be too upset about me. What I'm going to do is I associate what we call chamber here as torus. I know you'll be upset and that is not torus, but fine playing. But this is an analogy. So what we are thinking are those are we associate each maximum cone, what we call now a chamber, with a torus, and then we have those function here. And if we write it out, you can see it's 1 plus y, 1 plus. Let me use the custom notation. This is A2 and then A1 inverse. And then you can see this is actually basically the birational map we were just talking. So what we are doing is we have this torus and this torus, and then gluing between the torus are given by the wall function in this scattering diagram. That is how I kind of say this is an analogy to the fan picture in the toric world. And then it's like what I say here, the function gives us wall crossing, that is the gluing. And then here, gluing up of this 5 tori, then this is something what I call the A cluster variety of type A2. And then this, even though I'm just working with one example only, but in general, this is how you can define a cluster variety. And then the next thing is, if you're a cluster people, you'll ask about cluster variable, cluster monomial, but I know this is an algebraic geometry conference, so you might ask what are the functions, like what section line bundle here for this space. So here comes theta function. Like in the first page, when we're talking about the analogy, we're talking on the fan, each pawn gives us a toric monomial. And this is very similar here, which is to each pawn on the lattice. The third is again just for technical difficulty, technical reason. For each pawn on the lattice, we associate something we call a theta function. Theta function is defined something by Bossinger. The definition is very long and very combinatoric, so but you can understand it by just one reason, like one example here. Again, this is the A2 type, and then now I want to associate function to this pawn -1, 0. And the interesting thing is we kind of think of the pawn as a and a slope. It is like, you know, this vector space class we have. So what we are doing is we are like thinking this pawn as a slope, but we take negative direction of it. So it's something like that. And to define a theta function, like correspond here, we say the initial chamber, but like, and then we fix this initial slope and we kind of fix a end pawn, and we just want to find a way to get to this Keel. And what's meant by broken line here is when I have a line here, it might bend or not bend when we cross over a wall, but it can only bend over a wall. So here to arrive this pawn, in the next line you can see we can choose not to bend, but we can choose to bend. The wall crossing is you can kind of think as I just add the exponent here, and then here I have this direction associated to this line, and then I add it, I got -1, 1, which then my slope change accordingly. And one thing to note, it is not for the first part of the top, but the second part of the top is in this two-dimensional case. Actually, when we add it up, you can see I have arrow to the scattering diagram, because here when we add it up, we are on this two sides of the wall. I'm bending actually towards the origin, but then here you can see when I add -1, 0 here on this one, because I take negative direction, when I bend, I will just get away of the origin. So here you can see by checking the combinatory, there's only two ways I can arrive to this pawn here, and hence this gives us a theta function, which to this pawn Q initial slope -1, and then I have two final term to the broken line, and this is how we have for the cluster variety. And then what GHKK showed, maybe I should have one slide, is those theta function give the global section of the cluster variety. But the important part of today, what we care is we want to talk about the multiplication between theta function, because theta function itself can generate a vector space, but we want to see if we can have an algebra structure out of it. So what Bossinger, Keel, Kontsevich show is when we multiply two theta function, we can express it as linear combination of other theta function. Then this alpha PQR is our structural constant. And that here is the interesting thing is actually this alpha PQR can be expressed in terms of the broken lines, which is this long one of definition here, but actually it's very easy to understand it, which is let us do this example of multiplying this -1, 0, 2, 1. And then if you do the computation, do the calculation, brute force calculating it, you'll get 1, 1 and 1, 2 here. And then this is the picture, I guess some of you might have seen already. How we can see is, you can see this I just mean initial slope of the broken line. So here is, I have my P and Q give the initial slope of the two broken lines. So it's the initial slope here. And then here is, I have my endpoint is this out. So this is the endpoint here. This C is just means the constant to, because sometimes maybe we have some other number associated to the monomial. So those C are just the constant to the monomial here. And then like this final condition is just like we call it balance, but the other way you can see is actually is describing we have a tropical curve. Just it's like the final slope. I think the final slope equals to this direction. But anyway, you can see here this, the one thing just take home, like the take home message is this structural constant can be expressed in terms of broken line with initial slope given by this P and Q, and that this structural constant will give the space of theta function and algebra structure. And later on in the second part of talk, we might go over and say why we really care about it. And then here again the analogy, toric cluster fence getting diagram and toric monomial theta function. And then in the beginning we have convex polytope, and the analogy here will be something we call the positive polytope. And positive polytope, the definition is almost identical as what we have before, which is it might not be a polytope, we call it a subset, is positive for any P in layer A, Q in layer B. And then if we have something appear in our multiplication, then we want our R is in the A plus B layer. You can see it's exactly as what we were doing in the toric world, other than we replace the toric monomial to theta function. And those are just the notation for completing the story. Because here I can take the lattice either M or N. So the analogy here, we have convex polytope to positive polytope. And the next thing you can see, when we were doing the overview in the beginning, I emphasized we have convex, and the convex is like given by line. And now let me convince you the convex here in the cluster world is something is given by broken line. Okay. So this is what Magee, Najera-Chavez we propose. We got a closed set to be broken line convex if for any 2 points in the set, it is exactly like the convex which is in usual, we say any line joining X and Y will contain in the set, but now we'll say every booking line segment with endpoint or connecting X and Y will be contained in the set. And you can see immediately we can draw this conclusion. The very natural thing you want to have is this is a positive polytope that is a positive set, which is in the toric world is the convex polytope. Then we want to have convexity that is if and only if we have broken line convexity. Okay, let me say it again, which will say that we have the set S is positive if and only if the set S is this broken line convex. And then the proof is actually the idea is very simple. It's very easy to describe. In the beginning when we describe this structural constant, you remember we emphasized that this structural constant PQ are having broken line with initial slope PQ, P and Q. The way to do is we construct the two broken line segment with, because here we want to talk about the polytope. And broken line convexity is about endpoint. So we just convert the initial slope into endpoint. This is basically the idea of what the article is about. But the main thing is here now we can give a, because you're going to see actually having this definition of positive polytope is actually very, it's not easy to find a positive polytope, but having this broken line convexity gives you something very combinatoric and very easy to check if a polytope is positive or not. So then here, once we get this positive polytope, we can do the same thing. We got a greater ring, and then we take a pause, and this is the compactification of our cluster variety. And then let's move on the example. This is the very first example that appeared in Grosshawking Keel Kontsevich. That is, here is the A2 scattering diagram. I take the generator of the way, and then if we draw it, and then if you check, then this is immediately positive. And you can further calculate this is by looking at the multiplication relation, then that will give me a diapason surface of degree 5. But it seems very easy here. Usually cluster variety later in the talk we'll talk about include Grassmannian or many other homogeneous space that the cluster people have been seriously working on it. But what I'm describing here is what we call the type without Wilson variable. And what the space are is actually, the definition of cluster variety is just union of torus is explicit or not explicit, because we just cannot tell what space it is. And this is the very first or only known case for without Wilson variable. And then actually when we move to B2, we are going to see like this, we can do the same thing. We consider the scattering diagram and take the primitive generator and then we join it. And by using this broken line convexity condition, we can see this is positive, or in the beginning, we use the Dinkin diagram to show positive. And what we show is, this is, with Magee, we show that this is the diapason surface of degree 6, which is, even this case is like new already. And then, if you are like leave the algebra people, the next question is what's G2? And then we have the same scattering diagram. But here is the interesting part here. You might still want to take the primitive generator and then join it up like this case to give you a positive polytope. But it turns out that if you're naively doing that way, then this is not positive. What is even worse is if we take this 2 point minus 1 0 1 0 here, because like here the banding is 0 3. And so when you calculate the broken line, you figure out that you need to bend over this 0.03 half. And that you can see this is the interesting part because we obtain a non-integral pawn, non-integral vertex to those polytope, and this is just coming from this spoken-like convexity. But then here you might ask, if you're not a Custer people, or like you might ask why we care it, why is that interesting? Or even in the beginning, I would like, is that true, right? Is there any evidence we care something non-integral pawn, or like why we think about it other than we might just compute the space of this Custer variety? And here I want to give you the very first evidence, which William showed is for Grassmannian. They show something, the Newton Okounkov, like Grassmannian is one type of Custer variety as well, which the Newton Okounkov body of the X variety equals to the tropicalization of superpotential of A variety. Both of them are GLKN or GLN minus KN. There are many jargon here, but if you're into that story, you know what I mean. If not, I just want to say this tropicalization of superpotential are just the positive polytope we have been describing. And I think this Newton Okounkov body is like easy. It's like there's a way we can compute how that looks like. But it turns out that in the computation of Newton Okounkov body, there's appeared this non-integral vertex, like for the case of GL36, which is interesting to people. But with Lara Bossinger and all of us, we showed this non-integral pawn here. Here is just one slice of the scattering diagram of GL36. And those are the wall function, and those are the two Pooker. We have a value. We need to write in this way because there's a valuation to put the Pooker into our tropical pawn. But those are like, you can imagine those two pawn are just our like Pooker coordinate. And then the thing is, when we bend over this wall, we obtain this pawn here, which is exactly like what we have in the G2 case, that we have an integral pawn here, which coming from the spoken-like convexity. So you can see here, this thing really appear and give a reason why we have this non-integral bond in this Newton Okounkov body for this case. This is just an evidence, but then let me tell you why we care about, like in the beginning, why we care about this positive polytope. The thing we are thinking is we want to construct, everything is toric as we begin. It's like construct this toric model Batyrev mirror in this Custer world. The Batyrev mirror, the very first thing, what Batyrev do is he want to have a polytope to be reflexive. That is, the polytope is still a lattice polytope, and then you talk about the duality of the two polytope, and then construct the mirror space. So the very naive thing actually when we start this project is it's just like the A2 and B2 case. We just take the preliminary generator of the ray, and then we look at it as a pawn, and then we consider the convex hull of those vertices. And then what we show this naive with Magee, we show that this naive guess, this polytope is reflexive only for type A and B2. It's proof / not a proof. You can see that for G2, the polytope is no longer our guess. It cannot be positive. But here for type A and B2, we can even show those are reflexive. So you can see that give a good confidence that we can think about something about Batyrev mirror. And then here is like we can kind of generalize this Batyrev, like look at this weak weak toric Landau-Ginzburg mirror proposed by I don't know how to pronounce his name, Pezzo, Kontsevich. which is we are looking something from the superpotential, like in the Grassmannian case, and look at the polytope. So in the toric case, we have a toric funnel, we look at the fan, we look at the generator, we sum it up, we have anti-canonical divisor. And the toric case, we have this log Calabi-Yau pair, we have the space and a divisor as well. And then in the traditional way, we have, like, I mean, this is the picture we described. We have the divisor coming from the way, and then we have the Landau-Ginzburg mirror, and similarly, we have the divisor correspond to theta function, and then we sum it, should be theta here. Let me fix this. You can see I copy and paste and forget. But sum up the theta function as our potential, and then here is the generic section of, because this is how Batyrev do similarly as well, generic section a mildly singular hypersurface, and we think the similar thing. But here is like we are talking about hypersurface, so the very natural thing is we can think about the level set of this superpotential, and then the thing to mirror is we want to see this, because this potential is define the mirror, so we want to see this W, this function a section of some mirror space, some mirror pair here, so we want a similar thing working here as well. Sorry, this is U chat as well, just forget, because here is U is x minus d, and then this is a dual. We just want something in the mirror, and then in this historical construction, what we are doing is we look at the Newton polytope of this potential, and we consider the toric variety that associated to it, and we claim this is what we have for the mirror. And similarly, what we are going to do is we want to construct this Newton polytope, but now with respect to the theta function of this potential, and we want to this one is the same condition, but here is how we are thinking about our Newton polytope. Here will be convex whole of those VI, but with respect to the Bossinger convexity condition. And then historically, here we have the sections are mirror, and we are hoping we have the same thing here in the cluster world. So this is what we are approaching. But you can see here what I have been, like, this is a mirror symmetry picture that we want to establish for this cluster world, but all I have been saying here are just on the algebraic geometry side, and you may ask like what happened to the symplectic geometry, maybe it's like something we construct, right? What can we say? And then here, as I say, I want to provide you with two pieces of evidence why this thing naturally also appear in the symplectic geometry world as well. And then here is here a cluster theory, there's like this notation of mutation that is in the algebraic geometry language. You can think of it as we just change our coordinate, but like we can think in the definition as the union of torus, which is we have one torus, how can we get a new torus? And there's this process called mutation, and we can describe this mutation topically on the scattering diagram. And that, because you can see here a polytope is drawn on the scattering diagram, so the polytope will mutate accordingly. And by the way, here in the example in the beginning, because I'm doing the A case, so the scattering diagram for type A2 is like that. But here is for the, here is how we start for the X case here, because this is a symplectic. It should be on the X side. That this is, but it's just a flip in this Venn2 example. But then when we mutate the scattering diagram, the polytope mutate accordingly. But you can also see, as we say, mutation is kind of change of coordinate in some sense in the custom world. This mutation, like the different mutated polytope, will give us co and co, another compactification. But this is boring because the underlying projective variety doesn't change because we are just switching the coordinate. So here, like actually I want to propose we have another type of polytope, and actually I guess that might be even more familiarized to people who are working with mutation of polytope. The heuristic way how to think scattering diagram, as I say, this is X, so I flip the way here, is we kind of imagine there's like this singularity, like singular Lagrangian in this Lagrangian fibration on this. Like, do you remember in the beginning I say that those are the incoming wall and outgoing wall? Like at the infinity of the incoming wall, this is how the my symplectic friend will interpret the scattering diagram. But the thing is, like, when you have this Lagrangian fibration, you can move your singularity around. So what you can do is you can say move this singularity, oh no, not this one, to origin, got something like this. And then what you end up is you can see we will switch this incoming wall to be the outgoing wall, and this is still the incoming wall because I didn't move. But what it has on the affine structure on the scattering diagram is we kind of cut out this piece. You can say B0 if you are symplectic geometry on our lattice. And so here is what we are doing is we have this monotomy on the scattering diagram that identified this with this way, and then you sort of chop out this piece in the lattice. So here is this, like, we have been playing around with polytope. So we have this polytope here, so we are like, hey, we move the singularity, and we have this monotomy here, and so we just switch apply the monotomy in this polytope, that we obtain a polytope in this way, something like that. And then here actually the space will change here. And then here you can see we can go back to the mutation cycle we have, because here we can still go back to this like mutation of the scattering diagram. And then you can see here, we kind of keep on flipping the picture, but it's still the same thing here. You can see this one, I got this one, and then this one are just the mutation of the scattering diagram. We can have this mutation cycle here, and it turns out that this mutation cycle, you can see the reason the color is not the same. If flip is not really drawn by me, but by Rinaldo, because this is something appear in his symplectic setup, which is what he got it from the symplectic mutation. That he got this Lagrangian compactification, which he add the Lagrangian singular Lagrangian fibration to this space. So you can see this is something that also appear in the symplectic world as well. And then here, the next piece of evidence is not exactly that much about polytope, but about the wall causing structure. That's why it appeared in our title. What we want to do is we want to do this family floer mirror to those like very similarly in this custom world. Family Floer Mirror was developed by Fukaya Episide, and what we are doing with Fusion is we are going to use this two construction. But the idea is very simple. It is like there's this Family Floer Mirror, which honestly not easy to understand by me, but I just like want to redo everything. Kind of what they do, we just like we interpret what the Keel mirror, And like we just change everything in the analytic sense and then fit the construction of the mirror. So this is what we are going to do. So let me give a super quick short description of the GHQ mirror, which is kind of, you can see that kind of appear in our Batyrev mirror thinking. So we have this log Calabi-Yau pair, and then we have Y is a smooth projective rational protective space, and then D is a string of divisor. And then from there, we can do a tropicalization of it to affine a affine manifold and the cone decomposition of B. And here, this is why I want to put the collaboration with Vienna's. When Vienna in, because here if you start with dp5 and this change of 5 minus 1 curve, and when you draw this affine, do this tropicalization, actually you get something like this. But then the affine here is, we emphasize this is an affine manifold. So the affine structure, actually, we need to have this monotomy and color this piece there. And then there we obtain a scattering diagram, but this is not the way we get it from the cluster world. How to make it short, to construct this scattering diagram is we have this wall and wall function, and the coefficient of the wall function comes from curve counting. But what Hawking Keel show is at the end, the two scattering diagrams are the same. But you can see here is this entirely, we will come from one space, we kind of curve, and then we have the scattering diagram, and then we do the same thing, which is we can define theta function on the scattering diagram, and then what Hawking Keel show is the same. We can define multiplication on the theta function, the vector space generated by theta function carry and algebra structure. And then what we can do is we have algebra, so an algebraic geometry, we take SPAT. It's like you can see in the beginning we have braided ring, we take Poch. Now we have a ring, we take SPAT. But the heuristic proposal is the SPAT of this algebra will be our mirror. So how are we going to reinterpret all this construction in the symplectic world? This is a very long table and not super precise as well, but I just want to give you quick, and you can see here the wall in scattering diagram, like what Yushin, my friend, will say is a loci of this SYC fibration bounding the holomorphic disk. And then we have the slab function, that is wall function here, that is, you can see is coming from Gamow written index counting. The coefficient there is, you can see counting of broken line or counting of A1 curve, but here is open Gamow written invariant of index 2 disk. And then the wall crossing here, that is, we are multiplying those 1 plus x inverse. If we translate it in this family 4 construction, we are talking the isomorphism of Maria-Cartan space induced by their isotopes. But as I keep on saying, like, I just, this project to me is I just want to reinterpret everything in the symplectic sense. So here we have this GHK, or later Hawking Keel Siebert mirror. In the beginning, when we define cluster, we have a lattice, and then we take the torus. So here we have the lattice, we define the polynomial ring associating to it, and then there we obtain the algebraic torus, and then we glue it according to wall crossing. And then here is like we just switch the polynomial ring to be T algebra. The torus is rational domain, but in the cases we are doing, it will be just torus as well, but analytic torus. The gluing is the same, we still glue by wall crossing. And the good thing is, because like to finish our construction, because the wall crossing you can see in this, in the A2 example, they're just a polynomial. So we can use the algebraic gluing live up to the analytic sense by Gaga to do the same gluing here. So you can see here what Yushin, Lin, and I did is the family Floer mirror of this two Calabi-Yau space, which is the hyperkähler rotation. Sorry, I have a double of rotation of the rational elliptic curve minus the two star or 3-star fiber. The mirror of them is actually basically what we demonstrate the A2 or B2 example. So when we do the same construction, it has a compactification, which are the sorry, it's very long. It's like the analytic way to see this DP5 and DP6, but you can see this construction is not compactified. So it's like they have the compactification, which is coming from this DP5 and DP6. So sorry, I guess I just speak a bit too fast, but that's the end of my talk. Thank you very much for being here, listening to my talk. And that's the end, and those are the articles if you want to recap it. So that's it.